Okay, so we'll get started on today's lecture. We'll briefly review the mechanism of dehydration. And then now that we know how to make alkenes, we're going to use them as nucleophiles to add two electrophiles, as shown by these crap noodles shown in here. So I'll explain what these sort of represent. You see this one with the two red balls is symmetric, and then this one with the orange and purple is not. And so that's going to create an issue for us in how these things add to alkenes. So now is where we're really going to learn the most reactions of the semester. So from now until the end, there's probably about 15 to 20 new reactions to learn. And so we're taking alkenes and then transforming them into the functional groups that we've already seen this semester. So we're going to flavor that through some of the questions. How do you figure out what adds where and what functional group it is by reviewing the spectroscopy. Any questions before we get into it? Okay, so dehydration of alcohols was what we left off on. So we'll write the whole mechanism on one slide. Talk about the issues, again, that occur when you protonate that alcohol, it leaves, you generate the carbocation, and then you have to make some decisions. And so, as I said, the E1 mechanism is where there's probably the most ambiguity, because you're probably going to get a mixture of elimination and substitution. So we had seen that the secondary alcohol, when treated with a strong acid in the presence of water, will undergo dehydration. So really, under these conditions, you really need a strong acid, and I should put in here heat. And the square bracket just means catalyst. So a catalyst is, again, something that will lower an energy barrier, allowing the reaction to take place or take place at a lower temperature. And it's not incorporated into the product. So you don't see any of the elements of sulfuric acid in the product. Since that's an acid, the first thing that is going to happen is a proton transfer, so the alcohol is a base. And I'm going to just write HA for sulfuric acid, where A is the rest of the molecule, essentially. So we protonate and this generates the oxonium ion. And then we balance the charge with now the conjugate base of sulfuric acid. So the charges are balanced. The OH is now transformed into a good leaving group, so it will ionize to form water. And now we have a secondary carbocation. So that just transfers. We started from a secondary alcohol. Now we have a secondary carbocation. We identify the beta carbons to see if we can form something more stable. We realize that really only the beta prime carbon can help us out here. And everything attached to that is methyl. So we're going to do a 1,2 methyl shift. And at this point, it's a one-way arrow because we're going to something more stable. So it does not reverse at this point. So there's the tertiary carbocation. So we have to redo the process where that's now alpha. And those beta carbons are the same, and now that's different, so it's beta prime. And so you look at where an elimination will happen. And so from beta prime, if you eliminate from there, you'll get the more stable or the more substituted alkene. So to show that, now we'll invoke that conjugate base to abstract that proton and reform the pi bond. If you eliminated from one of the beta carbons, so either of those CH3 groups, so I'll just say from beta prime, this would be from beta. And then that minor product, the monosubstituted, that would just come from essentially the secondary carbocation, where you eliminate from that beta carbon. And so those are the three possible alkene products. And really, I would say, conceptually, if you can understand major versus minor, that's more important than trying to say like exact quantities for yields. So now we've formed alkenes. So we know the alkene has a pi bond. A pi bond is weaker than a sigma bond. And what we're going to focus on today is now using the two electrons in the pi bond as a nucleophile. So outside of acid-base chemistry, we use the terms nucleophile, electrophile. The nucleophile supplies electrons, and the electrophile accepts them. Now, the issue that we'll have, you have two carbons of an alkene. And so we're going to look at different types of electrophiles. So for like hydrogen H2, both elements of that electrophile are H. So each carbon will get an H. If we have different electrophiles, say like HBr, one hydrogen or one carbon is going to get an H, the other is going to get a bromine. And then the question after that is who gets what? And what we've learned so far will help us guide in determining which carbon is getting what atom of the electrophile. I'll make a screencast on this slide separate, so I'm going to skip this one. But it is important in terms of putting everything together, so what we've learned so far. But now we're going to move into, so E2 and E1, that stands for elimination. Now we're going to look at doing addition. So these are all addition reactions. And it means just that you're adding elements to the pi bond. So to write it on here, nucleophiles supply electrons, electrophiles accept electrons. And in the generic reaction here, we have the alkene in the middle. And why this is going to get complicated is the alkene can be symmetric or it can be non-symmetric. So I've labeled those sp2 hybridized carbons as C1 and C2. And then if we're going to use the general form of an electrophile as, say, AB, so if they're the same thing, it would be like A and A. The issue now, as we see, you can go to the right or to the left. So if we go to the right, we see that carbon 1 is going to bond to A, carbon 2 is going to bond to B. Or we can form some sort of isomer of that, where carbon 1 gets B and carbon 2 gets A. So with the models, I'll just show you briefly. So here's, I'm holding now the 2 carbons of the alkene. So you have the p orbital, they overlap on the pi bond with electron density on the top and the bottom. So if your electrophile is symmetric, so say this is hydrogen, so H to H. Each carbon gets an H. So that's not too bad to figure out. But now, a complicating fact of that is there's the top and the bottom. So that's going to matter if the electrophile approaches from one face or the other. But since they're both H, it makes your life a little bit easier in a sense. But if the electrophile is not symmetric, like we have the orange and the purple, so this could be like hydrogen, this could be bromine. And in this alkene, we have H, methyl, ethyl, and methyl. So the alkene is not symmetric. Now, it will matter if the electrophile acts this way, or you flip it this way, because each sp2 hybridized carbon is going to get something different. Now, the other thing, in terms of how these things add, is the timing. So like for hydrogen, if they both add simultaneously, that's called synchronous. So they're adding to one face, so the H's are on the top. But in other reagents, you can add one thing first, and then the other thing comes from the bottom face to add. And so that's asynchronous, because they're adding at different times to different faces. So just through that description, hopefully you can see that the reaction coordinates are going to get a lot more complicated now. So we have who's getting what face it's adding from, and the timing of the reaction. So we're going to introduce a couple more terms to help describe these processes. Yeah.
If it's synchronous, does it have to be on the same face, or can it be same time, different faces?
So if it is synchronous, generally speaking, it has to be from the same face. So for the purposes of our discussion in this class, that is true.
Thank you.
So the first term we'll introduce here is called regiochemistry. So regiochemistry basically describes what carbon atom of the alkene is getting what element of the electrophile. So they can add in two different ways. So that's shown going to the right or to the left, where carbon 1 is either getting A or B, and then carbon 2, B or A. So that is regiochemistry. Now perhaps the harder term to understand is this, stereospecificity. I'll say it, but it'll become a little bit more clear after you learn some reactions. Stereospecificity is when you can look at the stereochemistry of the product and then infer backwards what you started with in terms of cis or trans from the alkene. And the connection between the two is the mechanism of the addition. So that term probably won't be as clear until maybe Friday or next Monday, when we get into some other reactions. So let me just highlight some things here. We'll go more into depth about stereospecificity, but what we'll talk about today is concertedness, and that means the timing. If they add at the same time, that's synchronous, or different times, that's asynchronous. So synchronous additions happen to the same face, so we call that a syn addition. Asynchronous, and now this is where it's a little bit more complex. You can get addition to the same face or the opposite faces. That would be anti-addition. So even though something is asynchronous, it can still be syn. And all of that relates really to the intermediates present on the reaction coordinate. So here's the menu, as it were, of some of the reactions we're going to start to learn. As you can see, the fire hose is not fully open, but it's getting fully open. So you're now drinking from the fire hose, as they say. Even though it's a lot of information, the concepts of the mechanism overlap quite a bit. And so really what you need to be able to do now is, again, diagnose the nature of the reagents to help you understand what the mechanism is and then predict what the product is. So what is this, chapters 8 and 9 now, I think. We're going to walk through these basically over the next couple lectures. The unifying theme is that we're starting with an alkene, and we're going to do a functional group transformation using addition mechanisms. For the most part, the names, as you see in the first column, will help you predict what the product is. So hydrogenation, the electrophile is hydrogen H2. You get an alkane, and that's a synchronous reaction. And then the last three, for the most part, generalize if you're forming a carbocation, what the regiochemistry is, and then what the stereospecificity is. So hydration is the opposite of dehydration. You're going to take an alkene and you're going to add the elements of water to it. So one carbon gets an H, the other carbon gets OH. Hydrohalogenation, you're adding HX. Halogenation, you're adding X2. Halohydration, you're adding a chlorine and then an OH. Hydroboration, if you look, hydration and hydroboration are essentially the same thing, but you're able now to better control the regiochemistry. Dihydroxylation, you're adding an OH to each carbon. Epoxidation, you're adding one oxygen to both carbons. And oxidative cleavage, your alkene, both carbons now become carbonyls. And I haven't updated this slide in a smidge, so there's probably 2 or 3 more that are going to be added to this. And all of the timing, carbocation mechanism stuff we'll go through slide by slide. So the first one is a pretty common reaction, hydrogenation. And so that's the addition of H2. So the alkene becomes an alkane. So again, unsaturated and now saturated. Experimentally, this is the reaction that you would run in the lab to determine degrees of unsaturation. So we talked a lot about that, just looking at a structure, counting pi bonds or rings. We talked about using molecular formula to determine degrees of unsaturation. This is how you would do it in the lab. Say if you had a powder or a liquid of an unknown substance and you wanted to start figuring out what it was. Because hydrogen H2 is symmetric, you don't have any issues about what carbon atom is getting what. They're both getting an H atom. So there is an issue of facial selectivity. Does it add from the top or the bottom? You look at the products to determine, okay, am I forming enantiomers, diastereomers? How does it play out? So over the course of all of these reactions, the test alkene that we're going to use is this one that's shown. So that's 3-methyl 2-pentene. So I picked that one because it's tri-substituted. And depending on the nature of the electrophile, it will better represent these terms synchronous, asynchronous, syn, anti, as we study the mechanisms. So hydrogen gas is the electrophile. The reaction requires a precious metal. So typically platinum or palladium is used. I need to get this word right. So AD. So the metal is generally adsorbed onto charcoal. So it really looks like it's like black dust. It's like charcoal dust. You sprinkle it in. You need a polar protic solvent. And then you pressurize your vessel with the hydrogen gas. So this is typically with a balloon. Or a tank. So with a balloon, that's 1 atmosphere. With a tank, you can pressurize it, assuming you have a nice vessel that will contain that. And essentially, you're adding H2 to those carbons. You can also use deuterium gas, so that's the isotope of H2. And then these would then become D and D. And so now that's a way to label those specific carbons with deuterium. Any questions? So mechanistically, what happens is the hydrogen approaches the catalyst first. The catalyst sort of holds on to it. Then the alkene comes and will add the hydrogen to the alkene from that catalyst. Yeah. What about it? So reaction number 2. So this is hydration. So we're adding the elements of H and OH to those carbons. So now we do have this issue of regioselectivity. If you look at the starting alkene, we said it was tri-substituted. So since it's not symmetric, it will matter what carbon gets H and what carbon gets OH. The two possible products are shown here. We have the major one, which is a tertiary alcohol, and then the minor one, which is secondary. So the conditions are dilute acid and water. So basically hydronium. And so as I highlighted with the red and blue, that's what we mean by regiochemistry. So each carbon atom is getting something different. The reason that the major product is formed is because it obeys Markovnikov's rule, which is highlighted in green. And that states the carbon atom bearing the most hydrogens gets the electrophile. In this case, the electrophile is H+. So another way of thinking of it is them as has gets, and the rich get richer. So the carbon with more hydrogens gets the hydrogen, and then the remaining carbon gets trapped by oxygen. So in terms of our mechanism, again, now we have two different sp2 hybridized carbons of the alkene. We're starting with an acid hydronium. So the pi bond has to supply electrons, and it can do that two ways. So maybe I'll say A and B. So if we use that pi bond and we protonate A, that leaves B as a carbocation. So the carbocation, again, is in a p orbital. And now if you classify that carbocation, it's tertiary. So we don't have to worry about any rearrangements or stability issues. So we're in water, and we also formed water. So that's the electrophile, and water is now the nucleophile. So that lone pair will come down and trap that. So this is an example of an asynchronous reaction. You have the H adding, you get an intermediate that is then trapped by water. So they're not adding at the same time. And then a final proton transfer with water from the oxonium ion gives you your major product. The minor product would result from protonating B. And so the reason that's the minor pathway is because that forms a secondary carbocation. So given the choice, you want to form the most stable carbocation first and then trap it. Another way of thinking about it is alkene hydration gives the most substituted alcohol. Any questions? So the next couple slides, we're going to review all these, facts. We'll digest it a little bit. Again, because, sort of in these chapters, Markovnikov is the dominating factor in a lot of these editions. Yep.
After it forms the product, is there any chance you could go back through the E1 mechanism to make the octane or no?
Yeah, so the question was, once you form this, can it then go backwards and dehydrate? Typically under these conditions, you're using a more dilute, less strong acid. So for dehydration, you typically want stronger acids with higher temperatures. So which form of spectroscopy would you use to identify the presence of the OH group? So that would be IR. Again, you'd have that really broad stretch from 3,500 to 3,000. That's really to the left of your normal sort of sp3 carbon H stretching. So as I said, now when we're talking about nucleophiles, electrophiles, the pi bond in these is going to be the nucleophile supplying the electrons. And the curved arrows always start from an electron source, whether it's a lone pair, so like the lone pairs on oxygen, or the pi bond, those two electrons. And once you add one thing to the alkene, if you're forming a carbocation, you want to form the most stable carbocation you can. And that's a fallout of the Markovnikov's rule. So remember this trend when you're deciding the regiochemical issue of what carbon atom gets what. So to walk through that again with these, with the green arrow, you're protonating carbon that has the most hydrogens. So that generates the tertiary carbocation. That's then trapped by water. So what I didn't show on the prior slide now is the water can trap from the top or the bottom. And that would make a difference if you're generating a stereogenic carbon. The higher energy intermediate, you're now protonating the carbon with no hydrogens. So that generates the secondary carbocation, which water can trap from the top or the bottom. And as you see with the stars or the asterisks, those denote stereogenic carbons. So the bottom structure, the tertiary alcohol, whether you trap from top or bottom, you get the same thing. The top one, you're generating constitutional isomers. I'll save my butt and say it that way. Constitutional isomers where each has two stereogenic carbons. Any questions? So we're going down to New Orleans. We're getting on the interstate. We're hitting the gas. So we're moving on to the next reaction now. So hydrohalogenation, for the most part, resembles hydration. Except instead of adding OH, you're adding now a halogen, but mechanistically it's still following Markovnikov's rule. So we have this acid HBr. And so again, that is acting as our nucleophile, or in this case, our base, because it's doing a proton transfer. That carbon is going to get the H. We generate the tertiary carbocation that's then trapped by bromine. So to highlight, so H goes there or there, and then the bromine goes there or there. So again, the major one is forming the more substituted bromide. So tertiary versus secondary. So assigning these partial plus, partial minus is always useful because it helps you start your curved arrow formalism. So if that's delta plus, it's attracted to something that has electron density, that's the pi bond. And so we start our arrow. We're going to protonate based on Markovnikov's rule. We break the HBr bond. So we have the tertiary carbocation, and now that's going to be trapped from the top or the bottom face. So again, this is an example of an asynchronous reaction. So that would be trapping from the top or the bottom. So again, Markovnikov's rule is going to dominate the mechanism and help you predict who's getting what. So how many unique carbon atoms does this molecule have? Does anyone disagree? So don't be fooled by the little Jedi mind trick here with this H. So that the stereochemistry might throw you for a loop, but actually that carbon is bonded to two ethyl groups. So it might look like there's a stereocenter in there or two, but there's not. So there's 4. So drawn another way, that's what that molecule looks like. So since that carbon 3 has 2 ethyl groups, those are the same. It has symmetry, and so there's only 4 unique carbons. So is this molecule chiral? The answer is no. So what analytical method would be used to identify the presence of the halogen? So mass spectrometry. So remember that bromine has 79 to 81 in a 1-to-1 ratio of naturally occurring isotopes. So what about the minor product? Is this molecule chiral? So for this one, the answer is yes, because now if you examine it, you have carbons that have 4 different substituents. So this is going to be a chiral molecule. And so as drawn, I'll put the H in here to help us out. What's the name with the CIP designations? So it's 2-bromo-3-methylpentane. And carbons 2 and 3 are stereogenic. So we have to figure out if they're R or S. So let's start at carbon 2. We have a bromine, an H, and then 2 carbons. So bromine gets priority 1, hydrogen priority 4. Then you have the 2 methyl groups, the 2 carbon groups. Carbon 1 is just methyl, and then carbon 3 has other carbons bonded to it, so that will get priority 2, and that's 3. So if we're connecting the steering wheel here, that's counterclockwise, so that should be S. So we've eliminated B and D. Now moving over to carbon 3, which is also a stereocenter. Remember, the important thing for this is you're first looking at the directly attached atoms. So there's an H, that's going to be the lowest. And now you have 3 carbons. So from those carbons, you now have to go out what's bonded to them. One of them has bromine, so that's going to be 1. Then you're between ethyl and methyl, so that will be 2. That will be 3. And then here's a mental exercise for you. You got to put your eyeball like right here. So you're looking down that bond. And then when you do that, is it clockwise or counterclockwise? Should be counterclockwise. So that's going to be S. So we can eliminate C. And then A would be the correct response. So if we have S and S, which one is the enantiomer? So remember, for the enantiomer, the designations have to be exactly opposite at each position. So that would give us the 2R, 3R. So we're doing I don't know what you do. I'm about 85 mph going down to NO when I have to travel. What's your traveling speed? Keep it about 65, do you? I have a radar detector, so I can go a little bit faster. So we're cruising now. We're on to the fourth reaction of today. And so now we're going to look at a symmetric addition using molecular halogens. So this is X2. So halogenation using X2. For the most part, chlorine and bromine are the most common. So F2, not so much. And I2, we'll say maybe. So there's no regiochemical issue because both carbons get an X atom. But now there's a timing issue. And the reason there's a timing issue with the halogens is their van der Waals radii are so large that they can't add at the same time. So essentially you get one adding, you form an intermediate, and then the other one will add. So this is an asynchronous reaction. And they do not add to the same face. So it's asynchronous and then an anti-addition. So you're either using Cl2 or Br2, probably bromine's more common because it's a liquid. It's a really nasty looking liquid to handle. Chlorine is typically a gas. Gases are harder to dispense. And the solvent is pretty important, so it's non-participating. I specifically bring that up because we're going to learn about another reaction where you're using halogens, but then you have a solvent that participates in the mechanism, and you actually see the solvent incorporated into the product. So as we see with our model alkene, using bromine, each carbon is getting a bromine atom. But now look at the way they've added. So when I write these things for an addition reaction, I try to keep those four atoms in one plane to tell myself that they have added in an anti-fashion. If you start rotating them and putting wedges and dashes, it's a little harder to figure that out. So when I've highlighted it like that, again, if you think of the Newman projection, if you're looking down that bond, you can see that they've added in an anti-fashion to give you a 180-degree dihedral angle. So there's nothing that will control, if you look at it, it says enantiomers. You're going to get both of them, so a racemic mixture. But how do we explain why that is? So for the most part, we're normally sort of looking at bromine as it's drawn, so like horizontally. But as I said, bromine's a pretty big atom, and this isn't the best size of sphere to represent that. So imagine these were like much bigger, like really big. So if they're big, they can't add both at the same time. So instead of approaching parallel, maybe it tilts it this way. So one of them is going to add sort of a perpendicular. One will add first, and the other goes away. And that forms an intermediate. And then you have this other bromine floating around. And it's going to come from the other side. Because this space is already blocked. And so that accounts for the anti-addition. So on the last couple minutes here, I'll use my artistic ability to the best I can to help show that. So this mechanism is a bit funky in the sense of, bromine has 3 electron pairs. So it's already, you can't really, for the most part, show delta plus, delta minus, because any sort of discrepancies like that would just be very transient. So we're going to have the pi bond attack. And at the same time, an electron pair from bromine is going to come down because we're going to form a carbon-bromine bond. One's going to come down, and then the third arrow on the grassy knoll, as it were, is going to break the bromine-bromine bond. So those 2 carbon atoms are both going to be bonded to that bromine at once. So that's 3 atoms. So to give you a clue, when that other bromine leaves, it's going to be this. It has 4 pairs of electrons, so it's minus. And that means that bromine then has to be plus. So things with plus charge end typically in onium. And since this is bromine, this is called bromonium. And so now you've blocked one face. The nucleophile is then going to attack from the other face. So it can do essentially either or. So if we say A, and this is what I mean by drawing the anti all at once. So I've opened up that ring now. That shows the anti-addition, and all I have to do is shove in the remaining substituents with their stereochemistry as it already exists. Just a couple more seconds here. If we go B, we get bromine up there, bromine down there. There's the anti. We put in the stereochemistry. and we end up with enantiomers. So we're going to wrap it up there for today. There'll be some more questions on this on Friday, and then we're going to get to these other reactions where we're adding different heteroatoms to the alkenes, and we'll talk about how you figure them out using the spectroscopic methods.